Question 2 says that you should sketch the graph of this. Now there's lots of ways to sketch graphs. There's calculus, there's tables of values, there's graphing by intercepts, and I recommend for this question that you do neither of those, that you instead use a fourth tool in your toolkit, which is to graph by transformation. When I look at this, I see relatively simple changes to what could have been this. I just see a timesing by 2, I see a subtraction by 5. They're relatively simple transformations. So first I'm going to sketch y equals e to the power of x. That has 3 key points. It goes through 0, 1. It goes through 1, e, which is about 2.7. And it goes through negative 1, 1 over e, which is 1 over 2.7, which is about 2/5. So this is the basic graph of y equals e to the power of x. Now there's 2 changes to this. There's timesing by 2 and there's subtraction of 5. Which of those do you handle first? Well, if your favourite number of, say, 10 was there, you would first power the e up by 10, then you would double, then you would subtract by 5. So both of these transformations are after the application of the main function. So therefore, you just handle them in BODMAS order. So first you handle the 2. What does a 2 do? Timesing by 2 is a stretch, and because this doubling would occur after the powering onto e, then it is therefore a logical one and a vertical one. So when I think doubling, that's actually what happens. So these black dots become these black crosses. And then, so that's that done. Now subtraction of 5. When I see a subtraction of 5, I think a shift. I think a movement downwards or to the left towards the negatives. This is also after the main powering functions, therefore this is logical and vertical as well. So everything just goes down by 5. So that was 2.7, this is about 5.4, so that's about 0.4. What I'm doing now is a crucial process of estimation. You can use a calculator if you want in Core 3, but I want to make sure that I know whether that should be above the line or below the line when I shift it down. That's 2, when I shift it down it'll be negative 3, and I said that was about 2/5, that was 4/5, so this will now be 4/5 above negative 5. So that'll be there. Now, we have to get the asymptote right. So that's y equals 0. I always recommend just transform the asymptote separately. Y equals 0. So key points on that. This, and this. You times their heights by 0. They're now these black crosses. So times their heights by 2, you now have these black crosses. And now move their heights down by 5. You now get these white circles, black circles rather. So there's your asymptote. And now I'm going to connect the other white circles, doing my best to mimic the original shape. So here's the final answer. I'm trying to make the asymptote look genuinely asymptotic, so getting infinitely close to this line without ever touching it. Even that's not particularly good, that kind of looks like it's flattening out at a parallel level, so that's not all that good. And now I'm just going to be Jolly sure to indicate what I mean by what's the final answer? So that's the answer to part A. Now, what happens when you put bars entirely around the algebra for an equation? Well, it basically takes the low bits and makes them high. Now, this is just for the sake of the video, so it's clear. That will stay the same, by which I mean I'm using red, which you won't be able to use in the exam. That was a -3, so that'll become a +3. And that was -4 1/5, so this will now become +4 1/5. And this point will stay the same. This asymptote will now become here. So that red one there is the answer for that. Now, I'm just going to look back and check that I've done everything in the question. I was supposed to indicate the coordinates of the point at which the curve meets or cuts the axes. I've done that for the y-intercept. So that's 0, 3. That's 0, -3. But what about this? Well, the next intercept comes from solving for y equals 0. So the power you have to put on an e to get an x is 5/2. So that's what this says. So that point there is ln 5/2, 0. So that's the answer to question 2. Now part B, we have to solve, but note that it's only worth 1 mark, so this should be pretty quick, this question. Also, that wasn't A and B, that was A Roman numeral 1 and Roman numeral 2. So you have to solve this, but it's only worth 1 mark, and it says deduce. Deduce and 1 mark usually means it's pretty quick. Okay, so they want to know when final black graph, this, is equal to final red graph. Well, there, no, they're far apart, there, no, far apart, there, no, far apart, there, no, far apart. They start coinciding here. So the answer is x is greater than or equal to ln 5/2. I'll just say that again. I'll just go scan the x-axis. No, red does not equal black. No, 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 no. Yes. Yes, 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 yes. Because as of there, the black graph is equal to the red graph. So that's the answer to part B. And what about solving this equation? So 2e to the power of x minus 5 equals 2. That's red graph equals 2, so I'm just going to check how many solutions I'm expecting. The red graph is at a height of 2 twice, there and there, so I should definitely get 2 answers out of this. How do I get two answers? Well, to solve a modulus equation, you pretend the bars aren't there. And then you pretend that they're completely encompassed by regular brackets with a negative at the front. And they're the two answers to part C. The exponential and logarithm work. So we got this graph, the exponential, we got this graph, straight line, intersected A, find the equation of the intersection point, so just solve two expressions equal to each other. Now my algebra skills are not sufficient to actually get x by itself here, but I can at least make it become more like this, which is in fact what I'm asked to do. So this has now got this has got a 20 minus x, this has got a 20 minus x, so this is good to go. So the power you have to put on a 2 to get a 20 minus x is x plus 1, so here I am expressing that as a logarithm. Oops, it's not that, it's that. Now use change of base. Which is almost done, I just need to take away 1 from both sides. Okay, so that's part A. We now express this as an iterative formula. And the first one is x0 equals 3. So you pump that through a calculator. And x1 turns out to be, so I'm just going to get rid of something. So that's 3.087, etc. And then apparently it's 3.080, and then 3.081. So that's the answer to part B. And then what about part C? Now, part A, coordinate A, point A was where the two intersected. And we now have to say what the coordinates of A are. Well, the coordinates of A are before the comma, whatever this was, as long as it's sensible. Does it look like it's roughly about 3? Yeah, it could be. Now, so it's 3.081, and then 17 minus 3.081. And note that they didn't say you had to prove that it was accurate to one decimal place. You don't need to do that procedure of substituting in the lower bound and substituting in the upper bound. This simply means report your answer to one decimal place. So the answer therefore is 3.1, 13.9. Note, by the way, that just because I got this from the mark scheme doesn't mean I can assume that there are little dots there, because 3.087 to 3 decimal places might have come from 3.086 ... but if you're doing it with a calculator that would have been fine. Equally, you would be wanting to be satisfied that this genuinely did round to 13.9, in other words, not making the mistake of using rounded answers in subsequent calculations. But anyway, the fact that this was only worth 2 marks fortifies me in my belief that this is just quite a simple part C. Question 8a, we have to prove this. But we don't have to prove all values of A. We only have to prove it for values where both sides are defined, so not math error. This side will be undefined whenever cos A was equal to sin A. In other words, tan A was equal to 1. In other words, a whole bunch of values, for example, 45, which is why you have this thing here. I think that is a cleverly designed formula to spit out all the values that ruin this by making tan A equal to 1. So for example, if you put a 3 in there, you would get 7 pi over 4, which would be, I think that's pi over 4, 3 pi over 4, yeah, it'd be 7 pi over 4 there. So yeah, that's an example of something which would screw the right hand side up and therefore would not be equal to the left hand side, because even if the left hand side was screwed up, in maths we say that screw up, that while it's tempting to say that screw up is equal to screw up, we decide never to say that. Anyway, this is all just a big long diversion as to why I'm only being asked to prove that this is equal to this for lots of values, but not for all values. In other words, not these ones. Just get rid of something. Okay, so what should I do? I could turn this into this, or this into this, or in rare circumstances, work with them both separately until they join up. It's generally easier to take something complicated and make it simple. So let's see if I can turn this into that. So right hand side equals cos A plus sin A over cos A minus sin A. Now what I'm going to do now is a super funky technique well, it's not a super funky technique, it's a general problem solving strategy, which is to think, where have I seen something like this before? And I see something like this every time I rationalize a two-term denominator. So I'm going to multiply by the conjugate. This is the funky part, because that will have an exceptionally good effect on the top. It's just squaring a bracket. And on the bottom it will lead to a difference of 2 squares, which is the absolute business, because that plus that is 1, that is sine 2a, and that is cos 2a. Unadd the fraction, and you now get sec 2a plus tan 2a, which is the right hand side. Now that technique there, that's exactly the kind of thing where a student thinks, man, how would I ever think to do that? And that is why Mrs. Montero and I both recommend doing every last question in chapters 6 and 7 of the Core 3 textbook, so that you don't have to think to do that yourself, so that you can have seen a couple of examples where the solution bank uses that, and you can therefore plant that into your little kit of tools for doing trigonometric work. You do not have to think about yourself. You can kind of learn that rationalizing the denominator by multiplying by the conjugate in a fraction technique as just a standard little technique, as if it was a chapter all of its own. So anyway, that's part A. Now, part B uses the same basic ingredients as part A. You should always try and notice that. It's usually a clue, especially when it says hence. It says hence solve, not hence or otherwise. They actually want us to use this. So, what it's saying is that instead of solving sec 2 theta plus tan 2 theta equals to half, it's recommending that I solve cos theta plus sine theta over cos theta minus sine theta equal to a half. So 2 cos theta plus sine theta equals cos theta minus sine. I've done 2 steps in one there. 2 cos theta plus 2 sine theta equals cos theta minus sine theta. So cos theta equals negative 3 sine theta. So therefore tan theta equals negative a third. Pump that through a calculator, you get a basic answer of sorry, I'm just cheating by looking at the mark scheme here, sorry. This is an exciting part of the video. It's a basic answer in radians of 2.82. Now remember to link everything to pi. So pi is 3.14, so that basic angle is this one, which makes sense because that's where tan negative, as indeed it is here. So that leads to this x-wing fighter. You like that one and that one. You do not like that one and you do not like that one. So your basic little angle to tuck there is pi minus 2.82. So if you now take that away from 2 pi, that will be that angle there. And I think the domain only wanted angles in a relatively simple range. So there are the 2 answers. You type that through a calculator, you type that through a calculator, and there are your answers. Okay, question number 4 is about water being heated in an electric kettle. The temperature is modelled by this equation. So that's theta is the temperature in degrees Celsius. Now this is not a strange looking algebra situation, so I can therefore assume that this particular modelling of the rise of temperature is just what I would normally expect from my knowledge of kettles, just my basic knowledge of kettles from having used them. What I'm doing now is just checking that everything I'm going to do is sensible. I'm expecting this graph to look something like this. It's not going to get up past 100, I know that from science. So I'd be amazed if the graph didn't end up looking something like this. I think there's going to be an asymptote at 100. Why do I say that? Because e to the power of x has an asymptote. So just by squaring this algebra with my knowledge of science from literally year 7 or before, I can be quite confident that this is the graph. Now, let's do the proper parts. So, part A. State the value of theta when t equals 0. Now, remember my graph was just rough. I'm going to do this properly with the algebra. So, if t equals 0 and theta equals 120 minus 100 e to the power of 0. Let's get rid of something else. Which is 120 minus 100, which is 20. So of course, I now realize that this graph was not quite right. So that's the graph now. It starts at 20. So that's part A. Part B. Fact. At T equals 40, the temperature is 70. So in other words, 70 needs to spit out of this equation. And they now want us to find lambda, which I'll now do. So the power you have to put on a E to get an 0.5 is negative lambda times 20. So therefore lambda equals 1 over negative 20 log E half. The reason why I'm writing that as a fraction is so I can kick in log laws. The reason why I have to kick in log laws is because the question told me I couldn't just get any old answer for lambda. I had to make it look like this, and this looks far from that. In fact, it looks so far from that that I'm just going to check my work here. Have I copied this properly? Yes, I have. Oh, it was t equals 40. But I think that's otherwise fine. Yeah, that's otherwise fine. Okay, so what can I do here? I can do a log law. So a negative power just turns a fraction upside down while doing the powering. Oh, made this far too hard for myself. All I needed to do was bring that negative. Okay, this is what I really should have done. That's 1 over 40 times negative 1 times log e to the power of log e of a half. So I'll leave the 1 over 40 there, I'll bring that up there. Clogging, students call this. And the negative power just turns it upside down. So there's the answer, and that's your A and that's your B. And C, when T equals capital T, which is some mystery temperature capital T, oh, it says it actually reaches 100. Okay, so that means that asymptote should be ever so slightly higher than 100, because apparently it does actually reach 100 there. Now this point that I've just made now makes me revisit what I earlier said about how this algebra and this asymptotic situation was a good modelling for this. If the asymptote's not 100, I can't really think what it would be. Well, it would be like 100.1 or 100.001. Also, I'm not sure whether an ordinary kettle really can make the temperature get to 100, but of course it can. Temperatures can get incredibly high. But then again, temperatures of water can't get incredibly high. But in any case, I now realise that the real asymptote for this is 120. That's my mistake. And that the 100 is below that. And so this is the value of T here. So what this is an example of where we use algebra that, if you looked at the global situation, would be unrealistic, but for the particular situation we have, we only need the algebra to apply for a part of it. And what somebody's decided is that this graph is a perfectly good model of what happens to the temperature. You do not need the algebra to apply over here, because that's when time is negative. We don't need to worry about the fact that if you continue this graph down here, it would get into negative temperature. Obviously, kettles can't freeze water. And so if we don't have to worry about this section over here, we also don't have to worry about this section over here. So in other words, the asymptote that I paid so much attention to 7 minutes ago actually turns out to be relevant. But anyway, part C is now the same as part B. Basically, it's just solving an equation. So out of the formula spots 100, pops 100. Now in circumstances where I'm just calculator happy, I might put a decimal in there, and I can put a decimal in there, but why not put the actual value of lambda that I discovered in there? Just to keep everything exact. I've got that right. And now I have to solve that equation. So negative 20 equals negative 100 e to the power of negative ln2 over 40t. 0.2 equals e to the power of negative ln2 over 40. So the power you have to put on an E to get an 0.2 is negative ln2 over 40t. 40 ln 0.2 equals negative ln2 times t. So negative 40 ln 0.2 over ln2 equals t. Now, you might be tempted to think that you can use a log law there. You can't. There's no log law that has two separate logarithms on top and bottom of a fraction. Oh, actually, that's not true. There is. That's the good old change of base. And then you just type it into a calculator and round it off to the nearest whole, and then you're done. And to that, in that respect, this was a bit unnecessary because you can type that just as easily as you can type that.